Swayam Prabha. Digital India. Educated India.
Good morning to all of you, and thanks for joining us this morning. So, as Neil was saying, the plan for the day is that I am going to talk about a couple of applications pertaining to game theory and mechanism design, which I particularly have looked into. Of course, there are plenty of applications of game theory, and by no means it's an exhaustive introduction, but nonetheless we will try to cover few of them, which I feel will give you some glimpse that once you understand the theory of games and also mechanism design, in which are all the different situations of real life, you can apply them or you can model them. All right. Okay. The first talk is related to crowdsourcing applications. All right. How many of you have heard this word crowdsourcing? I assume all of you. Okay. And so what is crowdsourcing? Let's start with that. Okay. And we will see two different applications within crowdsourcing, one related to geospatial sensing and another related to data labeling. Okay. So let's start with crowdsourcing. What is crowdsourcing? So this term was coined by Jeff Howe and Mark Robinson, who are the editors of popular magazine namely Wired, in 2005. So crowdsourcing is essentially, it involves obtaining the work, information or opinions from a large group of people who submit their data via internet, social media or smartphone app, right? So essentially what does crowdsourcing mean? That it is harnessing the power of people. Okay, so if you have large number of people, large number of humans, and you want to take their help in terms of accumulating either information or their opinion for certain tasks actually, right? We will see certain example. So the most important part in this setup is that people who are involved in the crowdsourcing, they sometimes work as a paid freelancers while other perform small tasks on a voluntary basis, right? So we will see some example. So incentive, because we are talking about game theory, and incentive is a very important part of the games, right? Design of games, and incentive is also an important pillar in the design of games and mechanisms, right? Our goal is to focus on the task where the payment or incentive to the crowd worker affect the quality of the work done. So essentially think of that there are large mass of population and I want to seek their help, okay, for various purposes. We'll come to that. So it's important in many times that you give them some incentives, maybe in the form of money or maybe in some other indirect forms actually. So then what happens is in such task, there is a trade-off. What is the trade-off? The trade-off between the work quality and the total payout. How much you pay to the people, because that only will ignite their interest in the task, right? Because you can't go and monitor each and every individual, how the work is happening, right? So in this particular line of work, we will look into two applications. The task one is geospatial sensing and the task two is data labeling. So let's go to the geospatial sensing. What is geospatial sensing? This is what let's start with. Okay, so what is geospatial sensing? In this task, we want to design certain incentive scheme for people to seek their participation in executing some time critical geospatial scanning operation. What does it mean? Time critical geospatial scanning operation. Okay, which means there is a large geopolitical area, maybe as large as the entire country, suppose, and you want to scan the whole country for certain purpose, right? Do you think that it's possible even by a single human being or single organization? It's not possible. Suppose if you want to scan whole India for some purpose, you want to detect what are all the pockets where poverty is below or high above certain threshold, or you want to know what is the disease outbreak in different parts of the country. In one shot you want to scan the whole country and you want to get that information, you want to sense. It's not possible, right? So then you have to take help of people. That's the better way to go, all right? So how does it work? So in many real life motivating scenarios such as search and rescue missions, disease control, terrorism prognosis. I am sure many of you know the Mumbai incident, how the terrorists were running across the streets of Mumbai, and had we known the location of them in just in time manner, probably some better action could have been taken. You know, they were just roaming around on the streets, right, killing the people. Okay, so you can imagine, right? Locating an expert or expertise, right? So all kinds of these things are, you know, some of the examples of the task. So any of these tasks, success depends on two aspects. Number one, participant recruiting their friends to expand the team. So how will you go? Suppose if you have to go to the whole country, right? And you want to find out which are all the cities or the location in India where some disease is outbreaking, or you want to scan the whole country. The terrorists have planted several bombs at several places, and you want to find out what are all the locations where, you know, terrorists have implanted bombs, and you want to detect them. Obviously, military cannot scan whole country. So you want to take help of citizen of the country. So if you want to do this manner, this combing operation, what would you do? There are two important aspects to design of any such mechanism. The first is that participants recruiting their friends to expand the team. So everybody should be able to or willing to reach out to their friends and bring to the fold, bring to the fray, right? Please join the party, right? Next, the next point is participant putting in serious effort to accomplish the portion of the overall task, okay? That's also important. Just recruitment is not enough. Everybody who is willing to contribute, they should put serious effort to make the mission successful, all right? That is second, you know, characteristics, then only such missions will succeed. So a properly designed incentive scheme can make the whole mission quite successful. All of these two objectives you can achieve if you have the right incentive scheme. If you give the right incentives to people, they will also be encouraged to recruit their friends for the mission. Not only that, everybody will also be interested in helping you searching and rescue mission, right, to their nearby area, all right. So how do we go about that? So but we will see that designing such a incentive scheme is somewhat non-trivial and a challenging problem, okay. So let's start with an important challenge. So I'm sure all of you know DARPA, right? This is like Defense Research Agency of United States, which funds the research across the United States, okay. They had very interesting challenge in the year of 2009, and this challenge is known as DARPA Red Balloon Challenge. What does it mean? Let me first give you some of those who are not aware of it. So the challenge was to identify the location of 10 balloons. So you can see in this picture, there are these red weather balloon. These are called weather balloon, which are like, you know, floated in the air at sufficient height. So like at least in couple of kilometer radius, people can easily detect, right? Many times you would have seen these advertising balloons, you know, floating around. So these kind of red colored balloon were floated across the, you know, continental United States in 10 different locations, and those locations were not revealed, that which point these 10 balloons are floating in the air, okay. But anybody who is in the vicinity of, let's say, couple of kilometers of that balloon, they can easily spot them, right? But DARPA did not disclose where the balloons are, but it is known that there were 10 balloons somewhere, like treasure hunt actually. You can think of like a treasure hunt. I'm sure all of you would have played at some point in time, all right? Okay, so what? So whoever locates all of them, the first will get a reward of $40,000. So the challenge was locating all of them is not enough. You have to locate them first, okay, earliest possible. That's where time critical part comes in actually, because imagine a situation where disease outbreak is there, or terrorists have overtaken a certain region. The time is of utmost importance. There is no point if you spot them after a couple of days, by the time damage would have already been done. So time is very important here, right? That's why they put this constraint that whoever spots all the 10 balloons in earliest possible manner, they will be given $40,000 as a reward amount. Very nice. What happens next? So of course balloons are spread across the continental USA, I told you, and it is impossible for any individual to travel to all the places and spot these 10 balloons. You cannot travel across the United States, right? So big land actually, right? And it's a time critical competition. So you have to be really crazy in terms of your approach, that if you are not first, then all your efforts are waste. You will get absolutely zero reward, right? So crowdsourcing with some help from modern technology is a natural approach, and in fact this was the motivation of DARPA to explore the possibility of uses of some of this information and communication technology which have advanced in recent time. How can you use this ICT kind of technology combined with crowdsourcing to tackle such problems which are of immense importance and use for society? Am I right? Making sense? Okay. So let's go. I mean, story is more interesting now. So who won this challenge? So it was the team from MIT Media Lab. MIT has one very interesting lab called Media Lab. You should go and read about it. Okay, they do very interesting work, very creative work. So this is MIT Media Lab, who were the winning team. So what did they do? Let's try to understand. They efficiently harnessed the collective intelligence and collaborative effort of a social network. And that's how they accomplish this task. Okay, so they design an incentive scheme which is geometric. They call it as a geometric reward mechanism, decreasing from leaf to the root. Let's try to understand what it is. Look at this example. Okay, suppose Alice is the person. Consider in this case Alice could be some team member of MIT who is starting this challenge, right? Who is like putting their stake on the game and saying that okay, we will start, we participate actually. So what Alice does, Alice recruits their friend, let's say Bob and many others, let us say. Then each of their friend, each of the recruitee, they are free to recruit their own friends actually, right? So you get my point. So this tree will keep on expanding, all right? And what happens is that anybody who spots the balloon, let's say in this case Dave, who happened to spot the balloon, and mind you that these friends who are recruited, they need not be at the same location, right? Because if you are a person, your friends may be at a different location in the country. You call up all your friends and say that I want to recruit you, would you be willing to join me? If they are willing to join you, as per MIT's record, they will become your, in this tree, they will be your children, right? Like that. Then whoever spots the balloon, they reports their location, that here is one balloon I spotted, right? Like treasure hunt, all right? So for example, let's say if Dave spotted the balloon, right? And here somebody else spotted the another balloon like that, right? So the scheme MIT designed was the following. There was a $40,000 reward out of 10 balloon. So they divided that 40,000 reward money equally across all the balloons. So per balloon $4,000. Now the idea was very simple. Whoever spots the balloon, he or she will get $2,000, right? The person who recruited that person will get half of it, and person who recruited this Carol again get further half of it. So it's a geometric reward. As you go from root from this leaf node till the root, and every successive step, the reward of the person become half of its children. Okay? So can you now tell me, even if it is an infinite length chain, suppose Dave is at infinite distance from Alice. See, practically you don't know what, although we know that it will be a finitely long tree, but theoretically speaking, even if it is infinitely long tree, right? What will be the total payout of this whole chain? $2,000 I am giving to the leaf node, then half of it to the parent, half of it to the parent. So it's a geometric series, right? So if you take 2,000 out, this will be 2,000 plus 2,000 by 2 plus 2,000 by 2 square, 2,000 by 2 cube, dot infinity. So it's a GP, geometric yeah. So what would be the value, total value? It will not exceed 4,000. Am I right? It will be at max 4,000. That's the beauty of geometric series. So you see, this is the very clever idea that you are not exceeding the total payout more than what is budget available to you. Still you are able to recruit the infinitely long chain, and moreover you are giving the highest reward to the person who is spotting the balloon, right? So can you see that in this scheme both the conditions are kind of satisfied. One is there is an incentive for you to spot the balloon, because if you spot the balloon, straight jacket you get $2,000 no matter where you are in the tree. Does it make sense? Number one. Number two, even if you are not able to spot the balloon, it's always better for you to expand this family, right? The tree below you, because if somebody spots, you will get some amount of money. Okay, even though it may be minuscule depending on how deep the tree below you is, right? But at least you will get some reward. So you are not going to lose anything by recruiting people actually, right? So this is the clever idea, and it did fantastic job, and they were able to spot all the 10 balloons, I guess, if I am not wrong, within less than 48 hours or maybe 72 hours or some such statistics. So you can go and read this paper. This appeared in Science, okay? One of the journal where everybody aspire to publish, right? If you are in engineering and sciences discipline. So this title is Time Critical Social Mobilization. How do you mobilize the society for various time critical applications? Okay, fantastic piece of work. Okay, so I mean it's nothing very fancy or nothing very clever or complicated. It's just a very smart technique actually, right? But it works. Okay. Okay. So what? Now let me ask you this question. What if we would have perturbed this around and we would have made it top heavy, in the sense that give highest reward to the root and then half of the children, next half to the next children, and so forth. Like here what is happening is the award money is highest for the leaf node and it decreases as you move up to the root. What if it would have been highest at the root, and if you go down it decreases? What's the problem with that scheme? Why did they not think? You remember that there used to be that company called Amway or something, right? I mean they do all these I think still it is there actually, right? Even many times these LIC kind of companies, they make the agents and further sub-agents and all that, right? Most of them are top heavy actually, right? The first person, they get higher reward than the people under them. Can you see? I mean, I would like you to put little thought. What could have been the problem with that scheme, and would that have been better or worse than this scheme? Yeah. Precisely. Very good. So think of it. If the reward is higher on the root side, what I will focus on? I will not focus much on actually executing the task. I will instead focus on expanding the tree, right? So what will happen? People will gather. Everybody is trying to gather everybody else. That's all, and nobody is doing work. Can you see that? That's what happens. Many of this scheme probably, right? What happens? I am always busy in hiring people. That's all. Everybody is busy hiring somebody else, but nobody wants to do work, right? Because who wants to spend money? I mean, even if I spot the balloon, if I am way below in the chain, I am going to get peanuts actually. Whereas hiring is much less effortful job for me. I'll just hire 5 more people and sit home actually, right? Let them spot. Still I'll get the money. Am I right? In fact, the probability will be much higher, rather than I go around and hunt the balloon. Rather than that, if I hire 10 more people and let each one of them hunt, the chances probability of getting balloon hunted is much higher, and I will anyway get the reward, right? So it becomes flop show actually. That won't work in practice. Okay, it may sound on the paper good, but in practice it will fail. All right. So yeah. Yeah, very good point. So we are coming here. So these are called attacks actually. So although this scheme looks very nice, the way I told you that top heavy is not good, but bottom heavy also has its own problem. Can you tell me some problem? This scheme has some problem. Okay. I can do some gimmick here and still make more money. Yeah. Sure, that's definitely a good point. That is one problem. There is another serious problem. Let me tell you. Okay. Okay. So I will tell you. So this is MIT scheme is one of the scheme. So there are any such scheme. If you want to design, you can't blindly take any scheme and work. Lot more thought is required. A scheme may look very simple, but lot more thought would have gone behind designing this scheme. Why? Because human participants of social networks are strategic. If you recruited anybody, everybody is like kind of autonomous agent, right? They are free will. What they will do, you have no control. How many people they will hire, whether they will invest more effort on hiring or whether they will invest more effort on spotting the balloon, you have no control. They are free will, they are free bird actually, right? and most of the time they would do the thing which they think is most beneficial to them. Am I right? That's the whole premise of game theory, right? These are all strategic agent. So, and also they can manipulate the system in order to maximize their own payoff, right? As we discussed in the top heavy approach, it's not beneficial for me to spend time and energy in spotting the balloon, rather it is beneficial for me to expand my network, right? But is that effective for the task accomplishment or not? That's what we have to think about actually, right? So there are two major problems with any incentive mechanism for an atomic task over the social network. One is called Sybil attack and another is called node collapse attack. Let's try to see what are these two attacks. These are the two important attacks we felt that any scheme is typically susceptible to, and one should make sure that these schemes are free from these kind of attacks. Okay. So what is Sybil attack? So let's go back to this MIT scheme. So look at this picture. Here is Alice who recruited Bob, and this is the chain recruited by Alice, Bob who recruited Carol, Carol recruited Dave, and Dave finally spotted the balloon. So this is the path, right? And here you see 2000, 1500, 250, right? Now, what is the reward of Carol here? $1,000, right? What can Carol do is that she may do following. She can create two fake nodes below it, right? Because how do you know whether that person exists or not? Carol can just say that I hired some person X, pretend there exists some person X. Obviously, you are not going to go and verify, right? That's the whole problem. And in the system, she can report that I hired X, and X is actually herself only. It's like fake account actually. Then X, she can log in from X account and can say I hired Y. Y is again she only. Then from Y, then she may actually go and say that I hired Dave. Okay, so if you are my actual friend, before directly hiring you, I'll hire two fake nodes, two fake friends who don't even exist, and make sure that my second fake friend, I make that node hire you. What will that make? Why that will be beneficial? I think it should be clear by now to you. Look at this. So this was a Carol's node, and we put two fake nodes below it, okay? And then this is again still the same node Dave who hired, who spotted the balloon. So how the reward looks like now? 2000, 1000, 500, 250. All these three nodes belongs to Carol only. Am I right? So what is the total reward taken by Carol? 1750. So just by creating two fake nodes, she is able to boost her reward by $750. That's the problem. Yeah. Any question? Okay. So let me just show the previous picture just for the, so this was the original diagram where Alice, Bob, Carol and Dave, right? And this was the reward scheme as per MIT's geometric reward scheme. Now here what happened, we added two fake nodes beneath Carol, okay? So this is how the new chain looks like, 2000, 1500 and 250, and all these three nodes, on the face of it they may look like three individuals, but essentially that is one individual, right? And then by doing this kind of manipulation, individuals are gaining the benefits actually. Nothing prevents in this scheme for Carol to add in fact a infinitely long chain actually, right? Okay. So what is the ill effects? So first of all, look at the Bob. He is like a collateral damage here, okay? For no fault of Bob, earlier he was getting $500. Now, because of Carol doing all these gimmicks, Bob's reward has gone down to $125. You see the point? So this is called externality in these systems, right? For no fault of mine, just because you are doing some gimmickry, my reward went down, right? So if I am clever enough before participating, I will suspect these kind of problems, right? That if I recruit somebody and my recruitee is smart enough and he or she recruits fake nodes, my reward is going to get affected, even though I am early in recruitment, right? That's the serious problem with this scheme. Make sense? Everybody is convinced? Okay. So what do we do? So this Sybil attack is undesirable because it increases the expenditure of the task owner as the Sybils are getting paid. So these are called Sybil nodes, okay? These fake nodes. And also it reduces the reward of the ancestor of the Sybil creating nodes. So that will piss off the people who are actually recruiting. They'll say, why should I recruit actually? Because somebody whom I recruit, they will in fact there to hurt me actually, right? Okay. So what do we do? Okay, then before we go there, there is this another thing called node collapse attack. What is node collapse attack? It is just opposite of that. So to combat the Sybil attack, one may think of naive reward scheme top down. See, in top down scheme, do you think that Sybil attack will be possible or will it make sense? Suppose if I am giving reward 2000 to root, 1500 and things like that actually. So there, if you create the Sybil nodes, what will happen, right? It will still be, so suppose if Carol here creates 2 more fake nodes. So let's say, for example, here the total reward money is $4,000 and we divide it in this manner. D is the depth of the node. So here D is 0, D is equal to 1, D2, D3. So this is called depth of the tree, and T is the total length of the chain, of the winning chain, let's say. So the reward scheme, suppose if it is something like this, $4,000 divided by 2 power D plus T. T is constant, this is the total length of the chain, and D is, as you keep going down from root node, this D will keep on increasing in the increment of 1. So this becomes a top heavy scheme. Can you see that? If you play around with different values of D and T, you will precisely get what we were looking for, right? So if I just make it independent of T, I just call it as a D equal to 1. From here, if I just say D equal to 1, then this will become half of the reward going to the root node, then D equal to 2, then 1/4 reward going to this node. I mean, various versions you can generate by playing around with the D and T actually. But by and large, this will be the top heavy approach, right? It's a parametric approach. You just play around with this parameter and you will keep on getting different varieties of top heavy approach, where the nodes who gets recruited earlier in time get more money than the nodes who get recruited later in time. So now, if you are thinking that probably that may reduce my Sybil attack effect, the previous attack which we talked about, that will be less prominent in this scheme. But then it has another effect, namely node collapse effect. What is that node collapse attack? So in this scheme, the 2 people may join and they may pretend themselves as a one common node. That will be beneficial. Why? Look at this picture. So here the reward of Alice is what? 4000 divided by 2 power 4, because this is my scheme, 2 power D plus T. Then the reward of Bob is power 2 power 5, 2 power 6 and 2 power 7. This is how it is decreasing, right? Now, what is the reward of Bob, Carol and Dave together currently? What is their reward? This is 4000 times 1 over 2 power 5 plus 1 over 2 power 6 plus 1 over 2 power 7. Am I right? This is the total sum of their reward together, correct? Now, if they collude together and they collapse themselves as a single node, their total reward will go up. How? So suppose if they all 3 collapse themselves and pretend that that is one single team, then now balloon has been spotted here. So what is the length of the winning chain? This is now just 2. In the previous case, the length of the winning chain was 4, right? I am talking about this scheme actually, okay? If you change the scheme, probably the flavor of the attack may change, but this is very broad scheme by and large actually, okay? We will see that. So then what will happen? Here the total reward is how much? Because the T equal to 2 and D equal to 1, that reward is 4000 divided by 2 power 3, which is larger than this earlier reward, okay? So if you design some scheme, any scheme, incentive design scheme you take, always there are some possible gimmicks which people can play and can behave in a way that it benefits them. These are the 2 attacks, and by no means these are the only attack. There could be several other attacks. One has to think. So what I am trying to drive home the point is that in any such mission, if you sit down and design an incentive scheme, it's not child's play. It may seem very trivial scheme that I'll give half of either bottom up or top down, but there are so many nuances. You have to be really think carefully before designing any scheme. You have to think from all angles actually, right? What kinds of attacks people can do on this scheme and how can we mitigate against them, all right? Now what we are going to do is, in rest of the talk, I am going to do little bit of a formal analysis of this situation, that fine, these are the possible, this is the problem in hand, I want to design the scheme, I know that it is susceptible to various kinds of attack, what's the best possible way out actually? Tell me, right? Okay, so let's try to formalize with this paraphernalia. So now we studied this node collapse attack, so let's just skip this part, this you all know. So now we want any scheme, any kind of reward, yeah? Okay. Nothing. Sure. So for example, here, let us say, Bob had recruited this node, we are not given the name, but in this chain, this node who was although recruited by Bob, and probably they would have put in effort also, but somehow were not lucky to get the balloon, in this scheme they don't get any reward actually, right? Sure, I mean, you may call it as, for example, people, so that is called guaranteed payoff actually. What you are saying is, the moment I am recruited, I am guaranteed that I will get some small amount of money no matter what we do. So there are two ways to look at this scenario, what you just now told. One way to look at it, for example, person like this node, what is the incentive for this node? Because these people may be very, discouraged that if I am not part of the winning chain, I am not going to win. So I mean, I'm not sure whether I should even put in effort. But on the other hand, if you give this kind of guarantee that everybody will get a small amount of money no matter whether you are part of winning chain or not, then that's the other problem, because then I'll say that I am anyway assured of some reward, why should I put in the effort? You get my point? So these are like, these problems are always like, these are double-edged sword actually, and these are like always, if you try to fix one problem, second problem will pop up. And mind you that if you take any formal course on game theory and mechanism design later on, you will realize that this subject area has more number of impossibility theorem than possibility theorem, which means that there are more number of theorems which says that achieving this and this and this nice property in one mechanism is not possible. More number of such results in this literature than the number of results which says that okay, this and this and this good property are possible to achieve. That's the hallmark of this subject area called economics and mechanism design and game theory and all of them. If you undertake this formal study, then you will realize actually, right? Okay, so let's go here. So these are called desirable properties, okay? So what can we do? We put forward few desirable properties that we want a incentive scheme that should satisfy these properties, because these are good properties to have in our reward scheme, right? And one property we call it as a downward Sibyl proofness. So what does it mean? It reads the following manner: given the depth k of a node in a recruitment tree, a reward mechanism R is called downward Sibyl proof if the node cannot gain by adding fake nodes below itself in the current subtree. This is essentially what we discussed. So for example, if R is my reward mechanism, and how the R works, it looks at two numbers. So these are the two parameters input actually. One is the T is the length of the winning chain, how long is your winning chain, and K is the location of a node in that winning chain, right? So suppose this is some function, RKT is some function, you tell me whether the person is a member of winning chain or not. If the person is member of winning chain, tell me the length of the winning chain and the location of the node in the winning chain, I'll give you back the recommended reward. This is this function, and this is what we want to design. In MIT case, it was very clear what is RKT, right? MIT solution, we know what was it actually. Top heavy solution also, we saw what was it actually. So without loss of generality, let us say this is some function which you want to design, correct? Now, if this function were to be, Sibyl proof, then the following property should be satisfied. That for example, some node who is sitting at position K, like Carol in this example, right? And the T is the length of the recruitment chain. This is the pure chain. There is no fakeness involved in it so far. And if K recruits, let's say, n number of nodes below it in a fake manner, right? Then the total length will now become T plus n, because Carol has recruited n nodes, who are sitting at kth position, and she will take all the rewards at home for each position starting from I equal to 0 to n, right? So this will be the total take home reward, right? Whereas the current take home reward for Carol is this much. As long as you have ensured that my function R is such that this quantity is less than this quantity for all k and for all length of the winning chain, then this is the mathematical or formal way of saying that this mechanism is this Sybil proof. Okay, Sybil attack is of no interest to anybody. By doing Sybil attack, they can only lose actually, they cannot gain, right? Similarly, collapse proofness, we talked, like for example, if you had the top heavy scheme, we saw that if 3 people gang up together and make the team and pretend themselves to be a single team, that increases their total reward. And suppose you don't want that to happen, then this is the mathematical way of saying that if I have the winning chain of T, right, and if P number of people, now, so let's say given a depth K in a winning chain, a reward mechanism R is called collapse proof. If the user in the subchain of the length P lying beneath K collectively cannot gain by collapsing to depth K. So what it essentially means, if I look at the node at the kth position, the P nodes below it, all of these guys are ganging up together and collapsing themselves into a single node. So if they do that, then the length of the reduced chain will be T minus P, because the P nodes have collapsed, right? Original length was T and originally their total reward was this, right? Now their total reward will be the reward of the single node where they have collapsed actually. So this should be less than this, then this is called the collapse proofness, okay? So the question now becomes, does there exist any function R which satisfies this property, right? So we will see that something is possible, something is not possible, okay? Before that, okay, so we'll come to this dominant strategy later. So there is this something called strict contribution rationality. There is another desirable property, and this relates to her question she asked. So this says that we should ensure a positive payoff to the node belonging to the winning chain. So first of all, my reward mechanism should be such that every node in the winning chain should get something. Otherwise, there is no incentive, as she said, right? For example, even if I am part of the winning chain and if I get a 0 reward, suppose the scheme is such that if I am part of a winning chain and I may get 0 reward, then what's the incentive for me to recruit actually? So in order to avoid that, you may put this extra condition, namely RKT greater than 0 for all K less than T if T is the length of the winning chain. So this is called as strict contribution rationality. Now, there is this another thing called weak contribution and rationality, WCR. What this says, this ensures a non-negative payoff to the nodes in the winning chain. So look at this, the only difference between this and this is, here we are saying that the guy who spots the balloon, he or she should definitely get the positive reward, but any person above it in the winning chain may get either 0 or positive reward. This is little weaker condition than this, right? Because this condition always implies this actually. Am I right? If this is true, that every node in the winning chain is getting strictly positive reward, then this means that these two conditions will be true. But other way around need not be true actually, right? So this is called weaker condition of rationality, contribution rationality. The last condition what you may want to have is budget balance. So suppose DARPA had given you $40,000 budget. You shouldn't design a scheme where you end up spending money more than 40,000. Where will money will come from, right? So the total spend should be less than what is the funds available actually, right? So what budget balance says, the total award which you distribute to all the nodes in the winning chain should be less than equal to R max. And by the way, in this talk, I am assuming that any person, any node who is not part of the winning chain is going to get a 0 reward. That's still a point of debate, right? But we are currently focusing only on the space of those reward mechanisms where I will pay anybody who is part of winning chain. If at all you want to get money, you have to be part of the winning chain. Otherwise, there is no way you can get the money. This is my scheme. But even within that also there is an enormous amount of possibility. Top heavy, bottom down. Even in top heavy, how you should rate of decrease. In bottom heavy, how should be the rate of decrease as you go from bottom to top. There are so many variants possible. which variant is the best variant is what now we are trying to find out actually, okay. Which variant has a maximum amount of goodness into it. By goodness we mean some of this property. As many of these property they satisfy, the better it is actually, okay. All right. So, let's just now try to see few more results. So, some interesting results. I am not going to go into the proof of them. So, not all of these properties are simultaneously satisfiable, as I told you, right. So, let's see what is satisfiable, what is not satisfiable. So, first result we call is impossibility result 1. What it says is for t greater than equal to 3, no reward mechanism can simultaneously satisfy downward Sybil proofness, strict contribution rationality and collapse proofness. Matlab, this downward Sybil proofness, collapse proofness, these are the two attacks which we saw. If you want to have both of these two attacks completely missing, also strict contributional rationality means everybody in the winning chain getting the positive reward. All these three things, no matter which scheme you design, you cannot have all the three property at the same time. One of them will be violated for sure, okay. So, I am not going to prove it. If you want to know more about it, I can cite you our paper. You can read from that paper, okay. How do you prove that? It's an interesting proof. So, what is possible then actually? Let's ask this question, because this is sad news, right? That I cannot achieve, you know, this both the attacks. I cannot have a scheme which is free from both the attacks and also gives positive reward to every person who is in the winning chain. It's a sad news, right? Actually, that would have been a good thing. So, then what is possible? What it says is for t greater than 3, greater than equal to 3, a mechanism satisfied downward Sybil proofness, and I am just weakening this condition. Instead of strict contribution rationality, we will make it as a weak contribution rationality, and collapse proofness and budget balance if and only if it is a winner takes all mechanism. So, there is only one scheme called winner takes all. That scheme can give you all these properties, little weakened version of this SCR called WCR. So, what is the winner take all mechanism? This is a very silly mechanism. It says that a reward mechanism R is called winner take all if R max is greater than equal to RTT greater than equal to 0 and RKT equal to 0. What does it mean? Which means only the person who spots the balloon, they will get some positive reward, and up to the maximum cap on the budgets available, everybody else will get 0. So, that is called winner takes all. So, these are the popular schemes, right. In United States election you would have heard, right. In the president election there is this something called winner takes all, right. Whoever wins the vote, you would have seen in previous lectures, I guess, right. So, this winner takes all is one of the very important scheme where winner takes everything actually, right. No, anybody else will get nothing, right. But this is bad, because then I know for sure if I don't spot the balloon, no matter how much hard effort I put in to recruit the people, I am not going to get anything. But unfortunately, whether you like it or not, this is the only reward scheme which can satisfy all these properties, right. Any other scheme you take, one thing or other will get violated, okay. So, then what can we do then, right? This is a bit disappointing news. So, what we said is in this paper, there are two potential ways out actually. Either you relax the equilibrium definition, okay, Nash implementation you go. So, what does it mean equilibrium definition? See, so far what we talked about is that my decision is independent of what others are doing. Whether I should put more efforts on recruitment or whether I should put more efforts on balloon search, these are called equilibrium behavior, right. How the agents will behave, all these participants will behave. Once you propose this, float this reward scheme, the behavior of the participant in the equilibrium state is called the equilibrium behavior, right. Currently this behavior, all the definition which I gave, we assume that behavior of an agent has nothing to do with how others are behaving. No matter what others do, it is, I will do this way, this is my best interest. That is called dominant strategy equilibrium, okay. There is another thing called Nash equilibrium. Maybe if not in this talk, some other talk, I will see if I can introduce that concept. You can weaken that, although it's not relevant for this talk, but we are not going to go in the relaxation of the equilibrium concept. We still will be with the dominant strategy equilibrium. We will take a different route. What we will take a different route? We will relax the properties actually. So, for example, we will say that, okay, if you cannot make completely foolproof in terms of these attacks, at least give me the guarantee the attack cannot benefit somebody beyond a certain limit actually. You get my point? So suppose by recruiting the fake nodes, I know that I cannot 100% of the time I can be foolproof. People may still game the system, but I should design a scheme where even if people game the system by hiring people beneath them or by ganging up with the people above them, they cannot increase their reward beyond a certain limit actually. That's what approach we are trying to investigate, okay. So, what we will do, so we define this notion called epsilon downward Sybil proofness. What is epsilon downward Sybil proofness? So, look at this equation from here till here, right. This part we had seen in the definition of, this is Sybil proofness, am I right? This equation you saw, the Sybil proofness is this left hand side reward is the right hand side reward. This right hand side reward is obtained after creating the Sybils, and this is the reward without Sybil. So we did not, we just wanted this inequality to hold. But what we are saying is, fine, this inequality may not hold all the time, but if I multiply 1 plus epsilon factor, which means that by adding your, Sybils, you may get this much reward, which may be more than this reward, but it will not be more than 1 plus epsilon times this reward, okay. You can boost your reward, but you will not be able to boost more than epsilon times this actually, okay. Is it making sense, this inequality? So this we call as a epsilon Sybil proofness, okay. Now, let's try to understand what could be the analog of, so can we design a mechanism with bounded Sybil attack? Does there exist if I relax this property? Okay. So yes, there exist. So what it says is for all epsilon greater than 0, there exists a mechanism that is epsilon DSP, collapse proofness, budget balance and strict contribution rationality, okay. In the sense that all the people in the winning chain will get the strictly positive reward. It is free from collapse proofness, it is completely budget balance, and Sybil attack it is not completely foolproof, but it is cannot exceed by more than epsilon factor. That I guarantee, I give you, okay. Now, so how will those rewards look like? This is one scheme actually. So here is the idea. You give to the leaf node the reward amount 1 minus delta times R max. So R max, for example, in the case of MIT, it was $2,000, $4,000, right? And how much was delta there? Delta was half. Because if I put delta equal to half in the MIT scheme, the RTT, this is the reward of the leaf node who spotted the balloon, it was R max by 2. Am I right? It was $1,000 actually, or $2,000, sorry, right? So if delta is half, it becomes a MIT scheme. But here what we are saying is, there was no epsilon in MIT scheme. MIT scheme was not free from, this Sybil attack. In fact, in MIT scheme, some person by hiring an infinite length chain can double the reward. They can almost double the reward. So epsilon was how much there? 1. You get my point? In MIT scheme, epsilon was 1. Because by hiring infinitely long chain, fake nodes, I can almost double my reward actually. So suppose if you choose any epsilon which is less than 1, that's what you want now, right? Because otherwise MIT scheme is out there, you go and take it actually, right? But I want something which is less than 1. So then you take some delta which is of this type. So if you fix the epsilon, then your delta will get decided based on this epsilon actually. And then any of the internal node, any of the non-leaf node, you give delta fraction of the child reward. Like there we were giving half of it, right? Delta was half. Here delta will not be half, delta will be, and why delta was half? Because epsilon was 1 there. So if epsilon is 1, this is 1 over 1 plus 1, this will be half. Am I right? But if you take epsilon less than 1, let us say, then what you can do is, you plug in that appropriate delta here, and then again it's a geometric reward scheme again. It's just that you have to play around with the coefficients at the leaf node actually. Don't give the half. You start with some other constant factor and then keep going up with the delta fraction actually. Accordingly, you can control the Sybil attack. Okay. Now, what if epsilon goes to 0? Then it will be a problem, right? Because if epsilon goes to 0, which means it will be Sybil proof. But it cannot, it will be a problem actually. This scheme cannot have epsilon equal to 0. That's where in the definition it is written, it is strictly greater than 0. It's a bit crucial, think about it later on, okay. Alright, so I'll just skip this, we saw that. Now, so we can also define something called delta strict contribution rationality, okay, and winner security. So what is delta strict contribution rationality? This says that for some delta number between 0 and 1, every non-leaf node is guaranteed that he or she will get at least delta times the reward of its recruitee or reward of its children. So if I am the one who recruited somebody, I should be guaranteed at least some reward, some fraction of the reward of the person whom I hired. Otherwise, what's the incentive for me actually? So this condition you can impose by putting this kind of inequality that RKT is greater than or equal to delta times RK plus 1 into T, RK plus 1T, where RK plus 1T is the reward of the person whom I hired, right? And I should get at least delta fraction, then I'll not be upset at least, right? Similarly, RTT is greater than 0, okay? And so this we call as a strict contribution rationality, delta strict contribution rationality. Then last property we define is winner's gamma security. What does it mean? That winner should get at least good amount of total money available. Like in MIT case, there was $4,000 per balloon, let us say roughly, right? So the person who spots the balloon is assured that no matter how long chain I am sitting with, if I spot the balloon, I am guaranteed that I'll get $1,000. That's the beauty. Am I right? See, that's why there is an incentive. You don't have to worry whether you are, 1 millionth node sitting below the chain. You are still guaranteed that you will get $1,000. Sure shot in MIT scheme. And that was the motivation for people to go and hunt around the balloon actually, and not worry too much that how long below I am in the chain. Whereas a scheme like MWay and all, there if you are too below, your incentive may be low because major award will be eaten up by the guys above you, right, actually. So that's where we say that let's define some factor called gamma. It tells you that this is the assured reward actually, if you are the leaf node. Now we want to ask this question. So now these two schemes are, these two definitions or these two properties are an attempts to make everybody happy. The leaf nodes are happy because you are guaranteed to get certain reward. And even if you are not a person who had spotted the balloon, but if you recruited the person and whose recruitee further spotted the balloon, still you should not be unhappy because you are guaranteed to get certain reward than what your recruitee is getting. So these two are again very interesting desirable property, and let's see what happens. Can I achieve them along with those previous things? So the goal is to accomplish the task, and at the same time I also want to minimize my expenditure, right? So the goal is to achieve the minimum cost thing. So the gamma security property is essential, otherwise the solution would be all 0, okay? Because if my goal is to minimize my total expenditure, think of from MIT point of view, although I got the $4,000 budget actually, but if I can still save some money, that's good for me, right? Although I don't mind burning whole the money, but if I can get the same task done in a lower cost, then I better do that. Am I right? It's a common sense. But then the trivial solution could be that I give 0 money to everybody. But that's also not the solution, right, actually. So then we define something called this C, calligraphic C. This is the space of all the reward mechanism. Think of them as space of all functions of this type, R, K, T. This is the space of all possible functions over which you want to pick some function such that, first of all, the total cost under that mechanism is as low as possible, number one. And number two, it also satisfies all those niceness properties which we talked about, right? Leaf nodes, gamma security, non-leaf nodes, delta security, then epsilon Siebel proofness and whatnot actually, correct? So maybe I think in the interest of time, I will just summarize the result quickly, what is possible. So this is the one result. It says that if you define your delta, epsilon and gamma, okay, so gamma is the factor for the security of the leaf node. Delta is the coefficient to guarantee the reward from my child. If my child gets some money, I will get at least delta times of that. And then epsilon is that Siebel attackness actually. So for any given these three parameter, if they satisfy this inequality, this is little technical condition, then you can always get a mechanism which is not only satisfying all these three property, but which is also minimum cost actually. Okay, and the mechanism is very simple. This we call as a gamma delta geometric mechanism, where leaf node gets gamma times R max, and the non-leaf node or the parent node gets this amount, gamma times R max times delta times T minus K, where T is the total length of the winning chain, K is your position in the chain, right? So if you are more closer to the root, the K will be less, right? And if you are more closer to the leaf node, this will be more close to 0, this power actually, right? So of course it is a bottom heavy scheme, so you can play around with this. Let me just show you the picture, how does it look like? So this is how it looks like. If you play around with epsilon gamma, okay, with the different combinations of epsilon value and different combination of gamma value, these are the admissible value of delta. So any pair of epsilon gamma delta which is below this surface, this blue surface, right? You may be seeing this curvature surface. You take any point either on this surface or underneath this surface. For such combination of parameter value, epsilon, delta and gamma, I can give you a mechanism. You give me any point in this region, I will give you the scheme which satisfy all those three property with epsilon, gamma, delta property. But if you give me some point above this blue region, I will not be able to give you. Okay? And what is the scheme? The scheme is very simple, we saw. This is the scheme, right? This is the scheme for any given epsilon, delta, gamma. Only thing is they should satisfy this condition. So this blue region is essentially this condition. Okay? Now, so maybe so in this scheme, where does MIT mechanism sits? MIT mechanism, this point corresponds to MIT mechanism. The scheme which we saw, because there epsilon was what? 1, right? Because I told you that you can make your reward double. What was the gamma? Gamma means the leaf node is getting at least half of the total pot of the money. So this is half. And then what was the delta? The parent was also getting half. So you can see that this point is half on this axis, 0.5 on this z axis, and 1 on this axis. So this is precisely, this corner point is MIT mechanism. And winner takes all mechanism is what? So winner take mechanism is any point on this surface is winner take all. Why? Because if delta is 0, suppose if delta is 0, which means parent is not getting anything, then the child, right? So any parent will not get any reward, which means only child will get the reward. So any mechanism on this surface is a winner takes all mechanism, right? Okay, so in summary, what we are trying to say is, so we introduced the concept of collapse proofness. We also, which exhibit the conflict among the desirable property, we also studied that, and we propose an approximate dominant strategy implementation. So this kind of mechanism which I talked about, they are called dominant strategy implementation, because here a strategy of an agent has nothing to do with what is the strategy of the other agent, right? Which is not always the case, and that is why we study this concept called Nash equilibrium, etc., right? And one can only hope to satisfy only an approximate version of all this desirable property under dominant strategy. You cannot hope to satisfy all this goodness property at the same time, right, in these kind of incentive mechanisms. And then we also presented a cost critical optimization technique, that how do you get the best possible mechanism. So what are the other thing you can, if you are interested, you can also think about it, that how do you facilitate the learning from failure of one person in the crowd to enable succeed of others. What does it mean? Suppose I searched in this area and I did not find the red balloon. Like, I want others should not waste time actually, am I right? If I have already combed this area and I did not find the balloon, why should other again come and reinvent the wheel actually, right? So, these kind of schemes currently are very new. It is just that I am recruiting 2 of my friends, you are recruiting 2 of your friends. And it is possible that one of your recruited friend and one of my recruited friend, they both live in the same area. They both may be doing redundant tasks, both are searching in the same area. This is a waste of effort, right, actually. So the question is, can we invent certain, and all these things will require lots of these gadgets and software also into the picture. So can you make up a system where, you know, when you start doing some scanning and if somebody else has already scanned and reported, then you can avoid it further actually, right? That will help overall team actually, right? So, but then in that case, things become like this. Suppose I scanned this whole area, I did not found, I gave that information out, and this helped other to save their time, and they ended up spotting, but then I don't get reward. then I'll be pissed off. Am I right actually? See, even if I'm not the part of the winning chain, I scanned this area and I put out this information, the balloon is not in this area. And you are somebody who was recruited by somebody else, not in my chain, you are in some other chain. But you looked this information and you avoided this area and went to some other area where you found the balloon. You will get the reward, your whole chain will get the reward, but in some sense, you have some liability towards me, right? Actually, I helped you indirectly. But if I don't get reward, I'll be upset. What is in my interest to tell you this information? So these are called price of informations, okay? And very deep area actually. And how do you design the mechanisms? How do you facilitate the information exchange? And you price the information. How do you quantify the worth of the information or the wealth of the information? For example, if I am early in the game, imagine that this MIT Red Balloon Challenge has just started. I am very early in the game, I scanned certain area and I did not find the balloon. And then I report that, okay, look, here there is no balloon. Versus already 10,000 people have been recruited. And now I am scanning this area and I am telling that there is no balloon here. There is a different point in time, the same information will have different value. Can you see why? Because if already 10,000 people have been hired and nobody scanned this area and I scanned and I declared that there is no balloon, there is no treasure hunt in this area, I will save the effort of 10,000 other people or large number of people, I will avoid them scanning this area as opposed to, in the very early phase. You get my point? Also, there is another side to look at it. In the very early phase, if I say that there is no balloon, all those 10,000 people who would have probably stepped onto this area, I could have avoided their search also. So it's a very carefully you have to look and strike the balance. At which point in time, what information you are revealing, how to quantify the wealth of that information, and then how do you distribute the incentive properly. Very interesting problem actually. I encourage you to think about it. Okay? Think of a very simple treasure hunt games which you would have played with your friends in your school days or even now you may be playing, right? And if you don't find treasure in some location, the worth of that information, how do you quantify? And the worth of that information is also function of the time actually. Whether early in the game or late in the game you found that information, that treasure is not here. Okay? Maybe with this I think, is it a good time to stop, Neil? Okay. So we'll just stop here and if you have one or two questions I can take. And maybe after tea break then we'll start another topic. Okay? Yeah. In this particular challenge it is so actually. This was the DARPA's Red Balloon Challenge. It so happened that unless you spot all of them, you will not get the winning status. But I mean this was more of a, more of a, you can think of it as a more like a, to trigger the, research community, think about these kind of problems actually, right? It should not be taken in a very literal sense. This was a very starting challenge where, the idea of DARPA was to inculcate this kind of thinking habit among the researchers that look, these are the problem of society which we are already either facing or may become quintessential in coming years, right? So it's important for us to be prepared in a timely manner to gear our thinking and our effort to solve such kind of problems, right? These are essentially the geospatial sensing problems in a very time critical manner, right? The actual problem may have little different flavors, but the starting point was this, and then lot more research has gone into it. After that, people have taken different variants of this problem and different things actually, right? Okay, yeah. Yeah. Exactly, that's what I am saying. So this was a very important research problem. In fact, some people picked up this thread of research after that initial work of DARPA. Even in DARPA, they did not have this kind of mechanism. See, this MIT's winning team, they had put up a website where online they were making the registration. So suppose if you were recruited, you used to get some kind of, some code number. and that code number you have to go to their portal and punch in, then only system will recognize you and tag to your recruitee, right? Then again, if you recruit somebody, system will generate some key, and that key you have to send it to your friend, and the friend has to go to the portal and punch in that key. Then only system will recognize that. So even though there was no provision in that, as far as I know, in the earlier solution of MIT scheme, there was no solution for somebody to upload this kind of information where everybody else can benefit. Even if it were there, definitely there was no provision to reward those people, that even my failure, it's not a failure, it's just an information. It's like a random variable, right? So I scanned it, it's just the random variable, so happened the balloon was not there. But then this itself, this failure is also very useful information. There was no explicit provision for facilitating information sharing, number one. Number two, even if you facilitate the information sharing, how do you reward for that information? There was also no such scheme actually. So I have not followed this literature of late, but I would encourage you, if you are interested, to do some research. This could be an interesting research direction to think about it and read the literature about it actually. Okay? Any more question? Okay. Okay, then let's stop here. Thanks.